Welcome to my YouTube channel. Our topic for today is the Hensel Lemma. We begin with our theorem, which states, suppose QS is a polynomial with integer coefficients. If QA is 0 and Q prime at A is not 0, then there is a unique solution K. Explicitly, if U is the inverse of the derivative at A modulo P, then K will be equal to minus U times QA over PD. The proof of this lemma is left as an easy exercise. Let's look at some applications of Hensel's lemma. Example, solve the congruent f of x equal to x squared plus 3x plus 7 equal to 0 using Hensel's lemma. Solution. Step 1, you will discover that mod 25 can be written as a product of prime. In this particular case, it can be written as 5 raised to power 2. Therefore, we start with modulo 5. And if it is true for modulo 5, it will also be true for modulo 5 raised to power 2. So, reducing the given polynomial, we are going to have x squared plus 3x plus 2 equal to 0. Now, our choices for values of x, which we are going to use to test the polynomial, will range from 0, 1, 2, 3, and 4, since we are in mode 5. However, if you check the values of x when it's equal to 0, 1, and 2, you are not going to get 0 modulo 5. But when x is 3 and 4, definitely you are going to get 0 mod 5. Therefore, the possible solutions will be x equal to 3 mod 5 and 4 mod 5. Step 2, we want to define our qx. The qx will be equal to x squared plus 3x plus 7, which is the given equation. Then you find its derivative, which will give us 2x plus 3. Now, we are going to check at when x is 3 and when x is 4, what is going to happen using our Hensel's lemma. Now, we are computing the derivative at point 3, mod 5. You're going to have 9, and that 9 is actually 4 mod 5. And the inverse of 4 modulo 5 is 4, which can also be written as 1 modulo 5. Now we'll compute our q at 3 modulo 25, and we are going to get 25, which is the same thing as 0 mod 25. Since q3 is 0, we'll conclude that x will be equal to 3 modulo 25. Will be one of the solutions. Moving forward, at x not equal to 4, q prime at 4 modulo 5 will give us 11, which is the same thing as 1 modulo 5. And the inverse of 1 modulo 5 is 1. When you compute q at 4 modulo 25, you're going to have 35, which is the same thing as 10 modulo 25. Computing our k, we are going to get minus 2. So, x1 in this case is going to give us minus 6, which is the same thing as 19 modulo 25. Therefore, we have two solutions, and they are x equal to 3 modulo 25 and x equal to 19 modulo 25. A second example, solve the congruent f of x equal to x squared plus 4x plus 23 equal to 0 mod 625. Don't forget, mod 625 can be reduced to 5 raised to power of 4. Solution. X squared plus 4x plus 23 equal to 0. like I said earlier, can be reduced to mod 5 raised to power 4. Step 1, you start with mod 5 and we first solve the congruence at mod 5. Factoring will give us x plus 1 and x plus 3 equal to 0. And when you solve for x, you're going to have x equal to minus 1, which is the same thing as 4 modulo 5, and x equal to minus 3, which is the same thing as 2 modulo 5. Step 2, we are going to solve when x naught is 2 mod 5. So define our qx to be x squared plus 2x plus 23. We check its derivative, which is 2x plus 4. And evaluating at x naught will give us q prime at 2 will give us 8, which is the same thing as 3 mod 5. Luckily for us, 3 is not 0, so we can apply our Hensel's lemma. When you compute q at 2, you're going to have 35, and which will give us 10 modulo 25. The inverse of q prime at 2 will be 6, or will be 2 rather. So, and the modulo, and that will give us 1, actually modulo 5. That is 6 will give us modulo 5. Now using our k, we are going to get minus 4, which will eventually give us 1 modulo 5. Thus, our x1 will be 7 modulo 25. Step 3, we do a similar thing with q7, and when we compute that, we are going to have 100 mod 25. Then q prime at 7 will also give me 18, which is 3 modulo 5. And our k will give us 17 modulo 25. Actually, it's minus 8, but minus 8 in mod 25 will give us 17 mod 25. Now, we have our x2 now will be 432 mod 625. Finally, our answer or result will be x equal to 432 mod 625, because that is where the question is asked. The question is asked in mod 625, not in mod 5. So at the end, you're going to arrive at a unique solution in mod 625. Moving forward, let's look at another example to show that there is a unique solution to the congruence x squared x cubed minus 2x plus 7 equal to 0. And the mode is mod 3 raised to power 2020. We will use our Hensel Lemma to show that there is a unique solution to the congruence. Step 1, we solve for modulo 3, and don't forget 3 is the base, so you're going to check for 0, 1 and 2 at most. Now, after checking, we discover that the possible solution will be when x is equal to 1, and that will give us 0 mod 3. Thus, the only solution here is when x not equal to 1 mod 3. Step 2, we check the prime of x in mod 3. We will first of all define our f of x to be x cubed minus 2x plus 7, and this derivative will be 3x squared minus 2. So evaluating at x not equal to 1 will give us 1. Again, the prime, f prime at 1 is not 0, so Hensel Lemma is guaranteed that the solution can be uniquely lifted to higher powers of 3. You go forward to step 3, applying Hensel's lemma again. Then you are going to have f of xn will be 0, then there is a unique xn plus 1, such that f of xn plus 1 will give us 0. Now, the updated formula is given by k equal to minus u times f of xn over 3 raised to power n mod n, where u is the inverse prime of xn. Since our prime f prime xn will give us 1, its inverse is also 1. Finally, since Hensel's lemma provides a unique lifting at each step, and we start with a unique solution x not equal to 1 modulo 3, it follows that the solution is uniquely determined modulo 3 raised to power 2020. By induction, there is a unique solution X satisfying the given congruence. Thank you for listening.